Good morning, Year 10, and today we're looking at an extension of yesterday's lesson where we were looking at the electric currents flowing through a wire and the impact on magnetic fields. And today we're looking at how we can create a solenoid. So there are 4 learning outcomes, and each of those outcomes are tested on both the foundation and the higher paper. So if you wish to copy them down, pause the slide now. Let's move. So you can support your learning with the Caboodle textbook. We're still using page 160, 161. If you aren't using the Caboodle textbook, I do really think it's a fantastic resource. I'm not on commission, but it is a very good resource if you haven't really understood a Scooby-Doo what I've talked about. All right, let's move. So, okay, so look at my diagram. So in what direction is the magnetic current flowing in the diagram? It's flowing away from me because we can see the cross on the middle of the circle. Using the right hand rule, so Fleming, I didn't talk about Fleming yesterday, but it is Fleming. What does the thumb represent? There's a picture. It's the current. And in which direction do magnetic field lines travel? North to south, always north to south. Okay. And what 3 elements can be magnetized? Now this is elements, not materials, elements. So think very carefully. And it's iron, nickel and cobalt. Steel is not an element. Steel is an alloy because it usually contains carbon. Varying amounts of carbon depending on its use, just for information purposes. So if you increase the potential difference in a circuit, so that's the voltage, what will happen to the current? It will also increase as current is directly proportional to the potential difference, as stated in Ohm's law. Exciting stuff today. Right, so a solenoid, it's not as exciting as it sounds. However, it is a wire that is in a coil, okay, and that wire is insulated. It's obviously insulated so it can't electrocute you. And when a current passes through the solenoid, the magnetic field is induced, okay. Here is a diagram of my solenoid and it amplifies that magnetic field. It can be used to create an electromagnet when there is an iron core. How is it controlled? You may ask yourself. If the current is stopped, then the magnetic field is lost. It's really useful to be able to turn on and off your electromagnets, okay? That's really important, especially if you're running like a scrapyard, some of you might be doing, or an eye surgeon, which I hope some of you go on to become. Because there you can use the solenoid to turn on, remove the piece of iron so it's attracted, and then turn it off again. Very, very clever. If the current increases, so does the strength of the magnetic field. And if the direction of the current reverses, guess what? So does the magnetic field. So, properties of a solenoid. Inside the coil, here we've got a couple of lovely diagrams. And the magnetic field is strong because of the combined effect of the coils. So more coils, stronger the solenoid. It's good, isn't it? So the direction of the magnetic field is uniform, which means it's all in the same direction. Okay? Remember we talked about those magnetized regions. It pulls all those magnetized regions to flow in the same direction. The fields are parallel to the axes of the solenoid, and then outside the coil, what's going on there? Let's talk about that. The field lines bend from one end of the solenoid to the other, and they travel through the centre. It's very, very exciting. You can see this on the diagram. And the field lines are similar to that of a bar magnet. Exam question. We're going to compare our solenoids to a bar magnet. Let's think. 3 marks. Compare. Think, similarity, difference. So, compare, when we're talking about compare, we want to find the similarities and differences of 2 elements. There's 3 marks, so you've got to have two of one and 1 of another. You will not get 4 marks if you give 3 differences. So the key words to answer this question are uniform, parallel, north pole, south pole, magnetic fields. So, here's the answer. A bar magnet and solenoid produce a magnetic field with the same shape. Similarity, tick, 1 mark. The magnetic field lines travel from north to south and the magnet, but, and this is the difference, in a solenoid they loop through the centre and are uniform. Okay, The magnetic field strength of a bar magnet is fixed, whereas a solenoid can be you can alter by altering the current flowing through the wire. This is okay. If you haven't had time to write your answer, copy down my exemplar answer. It's fantastic. It will get you all the marks. It does what it says on the box. Right, so electromagnets. So an electromagnet is a solenoid, which can be an insulated wire wrapped around an iron bar. You've probably done this with a nail, because we have a lack of iron bars in school and nails are cheap. The current is passed along the wire and the magnetic field is created around the wire. You probably did this where you tried to pick up paper clips, because again, we don't have iron filings are a bit messy, and paper clips, you probably did an experiment where you picked up large paper clips, small paper clips, teeny tiny paper clips, and we then looked at those paper clips and talked about accuracy and all of those things that are riveting, and it's stuck in your mind and it's now embedded in your memory, just ready for the exam. If the current switches off, then we lose most of its magnetism. You might have remembered, you might have had to tap it on the bench, which I told you not to do with your bar magnets, by the way. This induced magnetism creates a force of attraction between unmagnetized and magnetic materials. So we could use it for sorting out iron, steel, nickel and cobalt from non-magnetic materials like aluminium. Yes, we use this in sorting out metals for recycling. Another practical, exciting use of electromagnets. Electromagnets are used in electric bells. I don't think we really have electric bells anymore. We're all digital, but let's not talk about that. If you go to an old person's house and they have an electric bell, or if you go to a school that has a ringy bell, if you went to Churchill Primary, they have ringy bells, and so does Mepham. They have ringy bells, where a little hammer hits the bell like in an old-fashioned alarm clock. That hammer is moved by an electromagnet. Exciting stuff, isn't it? So they can be used to switch on larger industrial equipment, and they can be used by cranes, recycling centres, scrapyards. Oh my God, it's like I read the presentation before I talked. Right, let's move on. So we're going to investigate electromagnets. I'm going to get you to watch another riveting bite-sized clip. It's not got my voice in it, apologies. So this is a prescribed or a required practical, not sure why we're using that word now, to test the electromagnetic strength and the impact of current. I want you to look at the bite-sized videos and you're going to answer these 5 questions. Some of you, fantastic, sending me your work every day. Some of you might have just been logging in for the first time and think, what is she on? Either way, I'd always like to see your work. Mrs. Corbett is sending shout outs all the time. It is fantastic. So have a go, pause the slide, write these questions down, then watch the clip and answer the questions. Here's the answers. So what safety precaution did the presenter give and why? He kept the current at 1,000 milliamps to prevent the wire overheating. We need to remember that the higher the current, the higher the resistance as well. We need to think about this in terms of Ohm's law, and we can use it for burning things as well when we pass a high current through a wire. What happened when the current was increased? The number of paper clips picked up increased as the strength of the electromagnet increased. This is a riveting bite-sized clip. You can see that it's also on a high budget performance. The number of paper clips picked up is increased, and the strength of electromagnetic is also increased. And which materials are made the best electromagnets? Iron and steel, because they can be magnetised and demagnetized easily. And why do you think plastic is suitable for the core of an electromagnet? No, plastic is an insulator. That's a really bad question, by the way. It's an insulator. It has no magnetic properties. So, some exam questions for you. Again, pause the slide, have a crack at these. So, I'm just going to put the answers up because I'm fed up of reading. And right. Pause the slide, give yourself a mark. Key points from today. Again, I'm assuming most of you can read.